Hi everyone, I'm Cheryl. In this problem, we're asked to evaluate three different limits if they exist. Let's go ahead and take a look at the first one. This is the limit as x approaches infinity of the rational function x squared plus 2 over x cubed minus 1. Now just to get a general sense of what's happening, what happens to this rational function when x gets really large? Well, if you look at the numerator, we're going to take a very large number, square it, and add 2. That also gets very large. The denominator, you're going to cube a large number, which gets large, and yes, you're going to subtract 1, but it's still a very big number. So the numerator is approaching infinity, and the denominator is approaching infinity. This is an example of what we call an indeterminate form. I don't really have a good sense of what's happening to the overall rational function, just because I can see what happens to the numerator and the denominator. So in order to evaluate this limit, we need to somehow rewrite this expression so that I can interpret what's happening as x gets large. The idea here is going to be to look at the highest power in the denominator. The term of the highest power is your x cubed. So I'm going to divide both the numerator and the denominator by x cubed. So this will turn into the limit as x approaches infinity of x squared plus 2 all over x cubed divided by x cubed minus 1 all over x cubed. Okay. Now I can take this more complicated expression and do some simplifying. Notice that in the numerator, I can split this fraction up into x squared divided by x cubed, which reduces to 1 over x, plus 2 over x cubed. And I can do a similar thing in the denominator. I'm going to split this fraction into x cubed over x cubed, which is 1, minus 1 over x cubed. Now, why was that helpful? Well, it turns out that as x gets really large, what happens to 1 over a very large number? It's getting closer and closer to 0. What's happening to 2 over a really large number? It's also going to 0. In the denominator, 1 is just going to 1. There are no x values here, so this is going to 1, and 1 over x cubed is going to 0 again. All right, well, what does that tell me? Well, in the numerator, it looks like the entire expression is going to 0. And in the denominator, it's going to 1 minus 0, which is a 1. I no longer have that indeterminate form. It's approaching 0 over 1, which is 0. So my original limit is 0. Okay, let's try this again for the next problem. All right, it's a similar situation. I have a rational function. X is getting very large. The numerator is getting very large. The denominator is getting very large. So again, I have that infinity over infinity indeterminate form. So I need to find a way of rewriting my expression. And I'm going to use the same technique that I did before, dividing by the highest power in the denominator. So in this case, that highest power is x squared. So I'll rewrite this as the limit as x approaches infinity of x squared plus 2 all over x squared divided by x squared minus 1 all over x squared. And I'm going to rewrite this, again, kind of like what I did before. So this is the limit as x approaches infinity. I'm going to split this fraction. I'll have x squared over x squared, that's 1, plus 2 over x squared, divided by x squared over x squared, which is 1, minus 1 over x squared. Okay, now let's see if that helped. As x gets really large, what happens to 1? Well, it just goes to 1. What happens to 2 over x squared? Well, as x gets really big, 2 over x squared gets close to 0. In the denominator, 1 is going to 1, and 1 over x squared is going to 0. All right, so what does that tell me? Well, in the numerator, I'm getting closer to 1 plus 0, which is 1. And in the denominator, I'm getting close to 1 minus 0, which is also 1, which means that this limit is 1. Okay, we're going to try this again for one more problem. In this example, we have the limit as x approaches infinity of x squared plus 2 all over x minus 1. All right, again, if you try to just get a sense of what's happening, the numerator is getting very large, the denominator is going to be getting very large. We have infinity over infinity, which is an indeterminate form. So we're going to try the same trick that we did before, dividing by the highest power in the denominator. The highest power this time is just the x. So we're going to write this as the limit as x approaches infinity of x squared plus 2 divided by x minus 1 all over x. And we'll rewrite my expression. This is x squared over x, which is just x, plus 2 over x. And in the denominator, we have x over x, which is 1, minus 1 over x. Okay, let's see if that helped. As x gets really large, what happens to x? Well, it still gets really large. It goes off to infinity. But 2 over x goes to 0. The 1 goes to 1, and 1 over x goes to 0. All right, so for the first time, I had a piece that was going to infinity. So I'm a little bit worried about this because remember, I didn't want infinity over infinity. But if you observe what's happening now, the numerator is getting very large. The first piece is going to infinity, and the second part is going to 0. So it's still getting large. But the denominator is no longer getting large. It's going to 1. So we have a very large number divided by 1, which is infinity. So this limit doesn't exist because of unbounded behavior in a positive direction. The values are getting larger and larger. Now, one thing that's kind of interesting to note is that if you are taking the limit as x approaches either infinity or negative infinity of a rational function, which is what we have in all three cases, there's a quick rule or a guideline to help you see whether the limit is going to be 0, infinity, or some number in between. And the rule says that if the degree of the numerator is smaller, then the limit will equal 0. And that's exactly what happened here. I have a degree 2 polynomial divided by a degree 3 polynomial. This limit will always go to 0, and that's exactly what we found out. If the degree of the numerator and denominator are the same, the limit will approach the leading coefficient of the numerator dividing by the leading coefficient of the denominator. Both of these are degree 2 polynomials, and so the leading coefficient is 1, and the leading coefficient here is a 1. 1 over 1 is 1. That's exactly what we found out. The last possibility is what happens if the degree of the numerator is larger than the degree of the denominator, which is what happened in this last case. When that happens, the limit will always go to infinity. I hope that was helpful. Thanks.